Thanks. All right, we are now recording. All right, so yeah, so you remember from the last class we talked about the addition of, let me see here. All right, we talked about the addition of HBr to alkenes in the presence of a peroxide. So okay. And what we said is that when we do a normal ionic addition of HBr to an alkene, the bromine bonds to the more substituted carbon. And there's a nomenclature for that, which is there's the Markovnikov product. When you attach the bromine to the less substituted carbon of the alkene, we call this anti-Markovnikov. So all right. And we said that this is a radical chain mechanism, okay? And radical chain reactions always come in 3x, right? And so the first step is always initiation. Okay. And the initiation steps are characterized by the formation of radicals from your initiator and starting materials. So all right. And so in the reaction here, this is the ditert-butyl peroxide is our initiator in that transformation, okay? And so we can draw a mechanism. So the way we draw these mechanisms for the radical reactions is a little different than what we've done before because we break it into these 3 acts. But we can still draw sort of separate mechanisms for each act. And so the mechanism for initiation involves homolytic cleavage of the oxygen-oxygen bond in the initiator. So I take a fish hook, push an electron in the OO bond to one of the oxygens, do the same on the other side. And what I end up with are 2 of these oxygen-centered radicals. Okay. We're going to spend more time on this, but remember that I said that, we can evaluate radical stability by considering the bond dissociation energy of the corresponding molecule with a hydrogen atom in place. And so if you look at the OH homolytic bond dissociation energy in tert-butanol, it's about 110 kcals per mole. And so that is a very strong bond. So what that tells us is that these alkoxy radicals are very reactive, okay? There's a strong driving force for them to find another hydrogen atom from whatever bond it can locate, okay? So that's the first step in the initiation, but we're not quite finished with that section. The second step is to form the actual radical that's involved in the propagation act. And so in this case, we're going to invoke the reaction of one of these alkoxy radicals with HBr. And to show that, I'll start with my single electron on oxygen, draw a fishhook, and start from the HBr bond and connect a fishhook there. So that's telling me that I'm making an OH bond, and each species is bringing one electron to that bond. And then, of course, I need to deal with the remaining electron in that bond. And so I push that to bromine. And so what I end up with is tert-butanol plus Br dot. Okay. So that is the initiation. In the second act, we have the propagation events. And these are the steps of the radical chain process where the starting materials actually get converted to product. So okay. And so in the case here, we're going to start with Br dot and have that react with my alkene. And so the Br dot is going to attack the pi bond. And again, we're going to use the fishhook notation. So a little fishhook from bromide, fishhook from the pi bond, deal with the remaining electron, push that onto carbon. What I generate is this alkyl radical. Okay. And in the second step of the propagation, that alkyl radical, so 1, 2, 1, 2, that alkyl radical is going to find another molecule of HBr and abstract a hydrogen atom. So start from the radical, draw a fishhook, start from the HBr bond, draw a fishhook, and then one more fishhook going to bromine, okay? And so that then gives me my product. Plus Br dot, okay? And an important point is that the radical that goes in is the radical that comes out in the propagation. So bromide radical goes in, bromide radical comes out. So okay, and so if you've written some propagation steps and you haven't returned to that first radical in the beginning of the first propagation step, you're not there yet, or you've gone astray. So when you do end up regenerating that radical, you know that you've kind of completed that propagation sequence. And this is sort of the basis of this idea that we call these a chain reactions, because once they get going, you just keep generating the same reactive intermediate, in this case Br dot. It finds starting material, reacts, finds HBr, reacts, regenerate Br dot, and you just run that cycle over and over until either run out of starting material or you start to get accumulation of termination events. And that's the termination is Act 3. So termination steps are basically anything that abolishes a radical. So radical in, closed shell species out. And the book has a lot of examples of these. One example is just to take two Br dot atoms, have them combine to make Br2. Okay, I'm going from a radical input to something that's closed shell in the product. So that disrupts the chain. I don't have that Br dot anymore to cycle through the propagation steps. And so the system stops. And basically we wait until we have another Br dot formed before we can continue with the propagation. All right. And, you know, a good rule of thumb is that under sort of typical conditions, you get about 10 to the 4 propagation steps for each termination step. So 10,000 molecules of product for each sort of annihilation of the Br dot radical in this case, okay? And that's a reflection of the fact that the energies of these radicals are very high and they don't form in very large quantities. And so you need to, they're sort of their collisions with each other are going to be quite infrequent. By comparison, in the propagation steps, we're having a radical which may be in very low concentration, but that radical, we're not asking it to combine with another radical, we're asking it to combine with starting material or reagent HBr in this case. These are molecules that are present in large concentrations. And so those reactions are much more facile, okay? All right, and so where we kind of left off in the last class was with the selectivity in the radical addition, in the bromide addition. And what we said is that there are two ways that an alkene could potentially react with Br dot. Okay. In the top reaction, we've got these things reacting to put the bromide on the less hindered position, and I form a secondary alkyl radical intermediate. In the bottom reaction, I form a primary radical, okay? And we said that the first pathway is preferred, and it's preferred for two reasons. One is that you have a kinetic effect. Okay, so it's faster it's easier for Br dot to attack the less hindered carbon. And, you know, this is a general, we talk about this idea of steric hindrance quite a bit in organic chemistry. You know, anytime you're reacting at a carbon center, if you think about an organic molecule, you know, carbon is like my body and like the hydrogens are my arms and legs and head, okay? And so the hydrogens are on the periphery of the molecule. The carbons are always kind of embedded. And so actually accessing those carbons, the ease with which any type of reagent can get to a carbon in a molecule is directly depends heavily upon its steric environment, how much stuff is around it. And a very reliable approximation is that things that have, you know, carbons that have less carbons attached are more accessible than those that are more substituted. Okay, so there's a kinetic issue, and then there's the thermodynamic issue, which is that the secondary radical is more stable. Okay, and I'm not going to redraw the bonding diagram that I drew in the last class. Hopefully, if I have time this weekend, I'll add this to the hyperconjugation handout that I made for you guys. But the orbital overlap is strictly analogous to carbocation hyperconjugation. So you have a C2p orbital interacting with an adjacent sigma CH orbital. That sigma bond, of course, is filled. It has 2 electrons. In a carbocation, that 2p orbital is empty. And so we let them mix and we generate a bonding and an anti-bonding orbital. In the case of radicals, the only difference is that I put 1 electron in that 2p orbital. And now when I mix, I have a 3 electron system. And so when I mix, I put 2 electrons in the bonding orbital. 1 has to go anti-bonding. That's bad, but I've still got 2 electrons that have been stabilized. So the net effect in aggregate is stabilization, okay? And again, I'll try to chem draw this out for you. It should be in your notes for Monday as well, all right? But so then this idea of radical stability is where I really want to kind of start this lecture. So, you know, this, when we talk about radical stability, you know, these are the question here. The question is the one that's preferred the primary alkyl radical? That is incorrect. The one that is preferred is the secondary alkyl radical. And the reason is that I have more adjacent CH bonds to overlap with that radical than I do in the primary. And so it's similar, you know, it parallels the carbocation stability. We said a secondary carbocation is more stable than a primary because you get more of this hyperconjugation. It's the same thing for radicals. And so hopefully that clarifies. If not, stick around and I'm happy to expound on it. All right, so we're talking about radical stability, which is, you know, a new term, and the way we can't, it's difficult to measure this directly. And so what we do is when we want to sort of quantitatively assess the stability of a radical, we actually look to its partner that has a hydrogen bound where that radical is, almost, you know, like the conjugate acid of a radical. It's not really correctly using the term, but adding a proton. And so that gets us to this idea of homolytic bond dissociation energies. All right. And so we've seen heterolytic bond dissociation. So that, for example, is when I take let's bring back our old friend acetic acid, right? And if I put this in water, we say that it's going to form acetate plus hydronium, right? And if I want to show that, I can just push those electrons onto the acetate, okay? So that's an example of heterolytic cleavage. Both electrons go with one atom. Homolytic cleavage, as you might gather, we put one electron on each atom. And so the notation is different. I use fishhooks rather than regular arrows, and I end up with two discrete radicals, okay? And so when we're talking about alkyl radical stability, what we like to do is look at the hypothetical reactions where I have R, which is going to be some generic alkyl group. I have RH, and then I cleave that bond, cleave the bond of interest homolytically, okay? And those numbers can be experimentally determined. And because, you know, the H dot part is the same no matter what type of CH bond I'm talking about, tertiary, secondary, primary. The differences in homolytic bond association energy are attributed to the stability of R dot, okay? And so I'm just gonna give you a table again. This, again, we had some of this data in the last class. Okay, so we can consider the four hydrocarbons that I've listed here. The corresponding radicals would look something like this. So this would be tertiary radical, and then secondary, primary, and finally methyl, okay? And so tertiary, secondary, primary, methyl. And then we can write out the BDEs in kcal per mole. Okay, and so this is about 93, 96, 100, and 104. Okay, and so what these numbers tell me, for example, is that primary radical 4 kcal per mole more stable than methyl. Okay, the difference here is 4, difference here is 3. Okay, and those numbers may seem small, but in reality they're not. 4 kcals is actually significant. It's a significant amount of energy. Okay, and so let me show this data to you in a more graphical representation. And so another way that I could draw this, for example, is with a free energy diagram. So okay, so I can place, you know, sort of ethane and the corresponding ethyl radical in H dot on the diagram. And the delta here is going to be 100 kcals per mole. Okay, so I would need to put 100 kcals per mole of energy into the system to cleave one of those bonds. All right, we can draw the same thing for, let's say, the tert-butyl radical. Okay, so the hypothetical cleavage of one of those CH bonds, and the delta there is only about 93 kcals per mole. Okay, so I have to put a lot less energy into the system to cleave the bond. The CH bond is weaker. The radical that's formed, the alkyl radical that's formed, is more stable. Okay, so hopefully that makes sense. All right. And so why is this important? So it's important to qualitatively know the stabilities of alkyl radicals. That's easy to remember. But also, if we know bond dissociation energies, we can actually start to calculate delta H values, changes in enthalpy for reactions. And, you know, this isn't sort of the full story, right? You need to actually think about delta G equals delta H minus T delta S. So there's a temperature and entropy contribution to the overall free energy. But the delta H term tells us if from an enthalpic standpoint, if from a bond making, bond breaking standpoint, if the reaction is going to be favorable. Okay. And so to have that discussion, I'm going to give you a small table of BDEs. You don't need to memorize these. If we ask for them, we'll provide the table, but we're going to use them in the discussion that follows. So I'll just write them out here. Okay, so we said that for methane, the BDE is about 104 kcals per mole. For something like ethane, where you generate a primary radical, so I'm going to kind of generalize this by saying primary CH is about 100. Secondary CH is 96. Tertiary is 93. And I'm using the approximate sign because, you know, we're not talking about specific molecules. We're just sort of drawing generalizations. For reference, a sigma CC bond is about 90, and pi CC, so just the pi component of a pi bond, is about 58. Okay. A couple more bonds that I want to show you. So HF is very strong, 136. HCl is 103. HBr is 88. And then primary carbon fluorine bond is about 111. Primary carbon chlorine bond is about 85. Primary carbon bromine bond is 72. Okay. And just for reminder, the diterbutyl peroxide is approximately 36. It's a very weak bond. Okay. So if I know bond enthalpies, I can calculate the overall change in enthalpy of a reaction. And this is valuable to a point. and I'll explain the point in a second. But it's valuable in the sense that it can tell me if the overall reaction is favorable. And the second thing that makes it useful is that I don't need to know anything about mechanism. So I can just look at the starting materials and the products, look at what bonds are broken and what's made. And if I have access to those BDEs, which, you know, there are tables of these things all over the place, I can then do an approximate calculation of the overall enthalpy of the reaction. So it's very useful. But again, there's an important qualifier, which I'll come to in a second. So how would we go about calculating the delta H? Okay. It's very simple. The enthalpy of a reaction is going to be equal to the sum of the homolytic bond dissociation energies of the bonds that are breaking. Okay, minus the sum of the homolytic bond dissociation energies of the bonds that are forming. Okay, and so the first term here is positive energy in, takes energy to break bonds. The second term, though, is negative because when I make a bond, I get energy out. That's always stabilizing. So okay. And so what we're looking for in terms of favorable or unfavorable reactions is the overall delta H of the reaction going to be negative or positive, okay? And so we can go back and do these calculations for HBr addition to an alkene. And what we're going to consider is simply the balanced equation. Okay, so we don't bring the initiator into this calculation, okay, and we don't need to worry about like termination. We just want to look at the reagents, the alkene plus the HBr, and ask if the change in enthalpy for addition of HBr to the alkene is positive or negative, okay? And so we'll use the table that I gave you, and we'll use this equation above. And this is about my upper limit in mathematical skills. So I really don't like doing this type of stuff. But all right, so we're going to go DH naught HBr plus DH naught pi CC minus DH naught secondary CH plus DH naught primary CBr, okay? So let me just unpack this for a second here, okay? So on the left here, these are the bonds that are breaking. So I break the HBr bond, I break the pi bond, and on the right then are the bonds that I'm forming. Okay, I make a secondary CH bond, I make a primary carbon-bromine bond. And if you then plug in the numbers, you get to 88 plus 58 minus 96 plus 72, okay? And if you do that math, you get out to minus 22 kcals per mole. Okay, so what that tells me is that the overall enthalpy of this addition reaction is negative. The overall reaction is favorable, okay? And this is very important. You know, you still have to worry about T delta S, but if delta H is very unfavorable, very positive, it's going to be difficult to actually run that reaction. You can't sort of beat thermodynamics. So the overall reaction is favorable, but the key point, the key qualification is that this says nothing about mechanism. It tells me nothing about how fast this reaction is going to go. So okay, and to sort of drill down on that for a second, I can consider the addition of HCl to an alkene. So okay, so I can add the HCl across. We're going to assume this is a radical pathway, and we're going to add the chloride to the less hindered carbon. Okay, and so if you do a delta H naught calculation, you have dissociation energy of HCl plus dissociation energy pi Cc minus dissociation energy secondary CH plus dissociation energy primary CCl. Okay, and go back to the table, plug in the numbers, you get to minus 23 kcals per mole. Okay, and so this looks like it's favorable. It is favorable, is the bottom line. But this reaction does not work. It does not proceed. If you take HCl plus an alkene plus an initiator, you do not get the product that I've drawn. You don't get a radical chain reaction under those conditions. And so how do we understand that? How do we rationalize that? And that's where you need to look at the individual steps in the reaction, okay? And so okay, and so I'm gonna switch to a new slide. So I've got everything that's coming here on the same screen. And so what we're gonna do is sort of set up a general reaction and then calculate the delta H's for each individual step. So instead of using chloride or bromide, let's just say we've got X dot, so halogen radical, plus an alkene. Okay. We know that the first step is going to involve addition of that radical to the alkene. Okay, to form an alkyl radical intermediate. And then the second step is reaction with HX. okay? And so the reason I wrote it like this is we can now calculate a delta H for step 1 and step 2 using both chloride and bromide. So we're going to make a small table here where I've got my halogen, so Br and Cl, and then I'll calculate delta H1 and delta H2, okay? And, you know, just like in our overall reaction calculation, to do this for the individual steps, we're going to just constrain our analysis to the bonds that are breaking and making in that step. So I'm going to break my pi CC bond in the first step, and I'm going to form a primary carbon halogen bond, okay? And then in the second step, I'm going to break the HX bond and form a secondary CH bond, okay? So let me just move these down a little bit here. Okay, and so if you go through the calculations, what you get here for bromide in the first step is going to be 58 minus 72, which equals minus 14. And what we get for the second step is going to be 88 minus 96, which equals minus 8. Okay, and so what does this tell us? For both steps of this process, when I'm adding HBr, the delta H is negative, okay? Both steps, so considering each step individually, each step is favorable, okay? But you'll see the difference with chloride here. So chloride is going to be 58 minus 85, which is still negative. In fact, it's more negative, so it's more favorable. That's great. But then if I get to the other calculation, I have 103 minus 96, which gives me plus 7, okay? And that's the sticking point, okay? And so let me put this on a energy diagram for you, and then I'll just explain everything again. So we can plot this. We can put Cl dot plus the alkene, okay? And that's going to go to Cl secondary radical plus HCl. So we have, okay. And so that is step 1. All right. And we know from our calculation that this delta H is minus 27. Okay. I can then draw the first step for the bromide addition. So it's going to be Br dot, oops, get rid of that, plus propene. Okay. And this is going to go to the alkyl bromide plus the alkyl radical, and that delta is minus 14, okay? And then the second step is where things kind of cross over. So I'm down here with my alkyl radical and HCl. That's going to find, they will find each other, and I will generate my product plus Cl dot, okay? And the problem is that this step is going to be uphill by 7 kcals per mole, okay? If I look at the situation for bromide, it's going down to something like this. So it's PR gives me the alkyl bromide plus regenerates Br dot, and then this delta is -8. Okay, so let me just clean this up a little bit so it's okay. So hopefully that's unambiguous. So basically what's happening here is that in both cases, I can do the first step. That's fine, no problem. The problem is that the second step for the chloride addition is uphill. And so I have to go from this low energy state or situation down here up to something that's higher in energy, okay? In the case of bromide, I go down in the first step, I get to here, and then I go down in the second step and I get to product. Yeah, Clayton, you have a question?
Yeah, I was wondering, like, since the first step releases like 27, is it like, why wouldn't it like just couple with the second step, and just because if it's only a 7, couldn't I just use like the energy from the first step for the second step, or how would no, it can't do that?
You get stuck because again, nature doesn't have a memory. You know what I'm saying? Nature doesn't remember that it just went down by 27. All it sees is that I have to go forward by uphill by 7. Yeah. And so it can't do that.
Thank you.
Yeah. Is that it? Okay. So basically it gets stuck. Another way to think about this is like, I'm trying to think. I was watching this movie with not Bill Murray. Was it Bill Murray? No. Who's the other guy that looks like Bill Murray? Forrest Gump. Was that Bill Murray? Anyway, that's Tom Hanks. That's Tom Cruise.
No, Tom Hanks.
Tom Hanks. That's right. Thank you. Tom Hanks is walking this little girl across the desert, and they get into this like fight scene with some guys that are chasing them. And one of the guys, they're fighting and they run up a mountain, and the guys are chasing him up the mountain. And then one of the guys starts rolling down the mountain, like he trips and rolls down the mountain. Okay. Simple. That rolling down the mountain is step 1. All right. Now, if I'm that guy and I'm lucky, I hit a rock. And to get over that rock and to go further down the mountain, I need to put energy in and go up. And that's the chloride situation. So the chloride gets stuck there. The bromide is like you're falling down the mountain and you fall right past that rock and roll all the way down. You don't have to put any energy into the system to get it all the way to product. Okay. And so, and this kind of gets a little bit to Clayton's question. So what does this mean, like in terms of like what actually happens? And what actually happens is that you get ionic addition of HCl across an alkene, the reaction that we learned in the last, in the last couple lectures. Okay. So the radical reaction suffers from this barrier in the second step. Okay. It just can't proceed. Okay. Instead, what's going to happen is that you're just going to have material that's diverted to the sort of ionic 2-electron process which is much more favorable. Okay. And so it's complicated. If it seems complicated, that's okay, because it is. But it's important to understand there are two ways to think about delta H. So the first way is the overall reaction enthalpy, and we need that to be negative, okay? But the second way, which is important, is that you need to consider the delta H of the individual steps, and you don't want any of those individual steps to be positive, okay? Because even though the reaction still might be thermodynamically favored, so we can see that, you know, for the HCl addition, if you're just looking at enthalpies, let's just put the T delta S term aside for a second. If you're just looking at enthalpies for the HCl addition, it's very favorable, right? Like the system would love to get there, but it can't because of that second step. So you can sort of tell if the reaction is feasible by looking at the overall process, or if it's favorable. How fast or if it will actually happen, though, is kind of a different story. And for that, you need to look at the individual steps. And so what I would encourage you to do, and maybe this is actually in the book, but I would encourage you to perform this analysis for HF and HI, okay? And see what answer you come to. We have all the bond association energies. All you're doing is changing the numbers and the reagents, but by going through that exercise, it may help to kind of drill all this home, okay? All right, I'm gonna stop there. We're gonna start the next class with, well, I'll do the virtual lecture with stereochemistry, which is very interesting. And I'll stick around for office hours. I'm gonna take a quick break, but I'll be back in 5 minutes, and I'll see y'all on Friday.